Hi, everybody. Sorry to interrupt, but thank you for coming to today's EERI seminar led by Dr. Huang Peng Hong. He's right now a postdoc at USC, but he just graduated with his doctorates from USC just last year. So far, his research interest has been in high-performance materials for civil mechanical engineering, especially with seismic resilient bridges and structures. Past research has improved the practical applications of smart alloys that can be used for next generation construction materials. Has developed two new bridge systems to maintain earthquake proof conditions under extreme conditions with extreme temperatures and corrosion. He's also published in 10 of the top journal papers, with 5 more in the pipeline. And he's also the reviewer of 6 of the top journals, such as Construction and Building Materials and Journal of Structural Engineering. So without any more, please go ahead.
Okay. Thank you so much, Nora. Thank you for the introduction. And hello, everyone. And first, I really appreciate Dr. Saidi and Dr. Petron's invitation, giving me this chance to be here. And also, everybody, thank you so much for your time. And it's my great pleasure to give this talk. Today, I'm going to talk about the advances in next generation shape memory alloy for actuators, dampers, and earthquake-proof bridges. Shape memory alloy in this presentation, sometimes it will be abbreviated to SMA, just for brevity. So first, I'll briefly introduce myself. I obtained my doctorate degree from USC and under the guidance of Dr. Genstad and Dr. Saidi. After my graduation, I worked as a postdoc in a structural and material research lab, and still under the guidance of Dr. Genstad and Dr. Saidi. And recently, I received the offer letter from Tianjin University, China, and maybe later this year, I'll join this university as an tenure track assistant professor. And the department I'll be working in is National Facility for Earthquake Engineering Simulation. It's like a Chinese version of the NES, the NFES. Here's some picture of this. This is a giant laboratory. As you can see, there's a person here. This is huge. And about this NFES at Tianjin University, now it has the world's largest regular and underwater shake table. It is larger than the one in Japan and the one at UCSD. So the size of the regular shake table is 66 feet times 53 feet, and it also has an underwater shake table, which is 20 feet times 20 feet times 200 feet. And back to this presentation, I'll talk about, again, the advances in next generation shape memory alloy for actuators, dampers, and earthquake-proof bridges. I'll present this talk in the following way. First, what is shape memory alloy? And also, what shape memory alloy can be used for? And the third part, the advances of the shape memory alloy applications in 3 parts: actuators, dampers, and earthquake-proof bridges. So first, what is shape memory alloy? It is a smart material. Smart material refers to the materials whose properties can be changed in a controlled manner by external stimuli, such as stress, temperature, photon, electric, or magnetic fields. So for shape memory alloy, its property can be changed by stress, temperature, and strain. So there are 3 parameters affects the property of this material. And other commonly seen smart materials includes piezoelectric materials, which can transfer stress into voltage, and also the photovoltaic materials, which can transfer photo into electric current, and also the ferrofluids, which can transfer the magnetic fields into motion. So smart shape memory alloy is just one kind of smart material. And secondly, smart shape memory alloy is a functional metal material. The reason why I need to emphasize that it is a functional material because compared with the counterparts is the structural metal materials. For shape memory alloy, we only use, they are usually not used alone to manufacture large structures, but we only use it locally when special functions are needed. So the conventional structural materials such as steel, we can use it to build the entire buildings and bridges, but for functional materials only locally, such as stainless steel, we use it to build the kitchen items, or the titanium alloy, we use it to build the engine blades, or for shape memory alloy, we use it locally. In this picture, it shows as the deformable engine nozzle. This orange plate is the shape memory alloy. So comparison with traditional metals. So this is a traditional metal, for example, such as steel or aluminum. Let's say if it starts from the 100% and by uniaxial loading, we load it to 110%. And after unloading, this material will end up with like 108%. There will be at around 8% of the permanent deformation. However, when it comes to the shape memory alloy, it has two cases. The first case, when it is under the high temperature stage, it will exhibit the superelastic effect. When it is under the low temperature state, it will exhibit the shape memory effect. For superelastic effect, if the same cases, if we start loading it from 100% and load it to 110%, and after unloading, this material will end up with 100%. It will completely recover to its original shape. That means it's like a big spring. And when it's under the low temperature stage, it will exhibit the shape memory effect. And the first three steps is the same: loading to 110%, unloading, it will end up with like 108%. And the magic thing is that if we heat this material up, it will completely goes back to the original shape. It's like this material can memorize its initial length. So that's why we call it shape memory effect, shape memory alloy. So here's what happens on the stress strain level and the microstructural level. So for traditional metals, it will, after yielding, if we keep loading it, and dislocation, relocation, and the plastic slip, all of these are irrecoverable. And if we unload it, it will end up with some permanent deformation, a residual strain. That means after unloading, this deformation, the plastic deformation, is not recoverable. However, for shape memory alloy, when it is under the high temperature stage and low temperature stage, it will be in different phases. In high temperature stage, it will start with the austenitic phase. It's a different phase, which is stable at high temperature and low stress. And if we keep loading it to some point, and if we unload it, it will goes back to the original location. That means it can recover all the inelastic strain and dissipates some energy. So the phase transformation from austenitic phase to detuned martensitic phase is completely recoverable, loading and unloading. And when this material is in the low temperature stage, we load this material from martensitic phase to detuned martensitic phase. Unloading it is just like normal steel, but if we heat it up, it can completely transfer to the austenitic phase. So the heating and cooling, this is phase transformation, not plastic deformation. So that's why this material can memorize its original shape. So here's the stress strain temperature phase space of the shape memory alloy in a 3D space. Normally for the conventional metals such as steel and aluminum, we only care about the stress and strain. When the temperature changes, its yield stress, ultimate stress will also change, but it's not as significant as the shape memory alloy. As we can see, this axis is the temperature axis. At different temperature, the material will exhibit totally different phases and totally different mechanical behavior. So the special thermomechanical behavior allows so many possibilities for this material. And here are some pictures of the shape memory alloy. This alloy can be available in the form of wire, strip, cable, and plates, and large size bars. The difference we cannot tell which one is, if I just give you a picture, we cannot tell which one is shape memory alloy because it looks like the same as the original metal. But from these pictures, what we learn is that, or from experience, the smaller the size, the easier it is to make, and the cheaper the size. The larger the size, the more expensive and more difficult it will be. And also compared with conventional steel, this is the periodic table. As we all know, the steel is made of iron, sometimes like carbon or manganese, sometimes with some chromium, nickel, or silicon. This is most of the steels, the matrix or the main elements are fixed. We know that the steel is made of this composition. However, for shape memory alloy, there's no certain composition for shape memory alloy. Any material or any alloy that exhibits the superelastic effect and the shape memory effect can be categorized as shape memory alloy. Here is all the elements, or the commonly seen elements that is involved in the shape memory alloy. And all the matrix material is marked by the bold red circle, such as iron, nickel, titanium, and aluminum, and also copper. That's it. So next I will introduce the development history of chip memory alloy. So far, chip memory alloy is available in mainly three groups: the nickel titanium based one, copper based one, and the iron based one. The nickel titanium based one is the earliest discovered one. So this the chip memory effect was first discovered in 1960s by NASA, and this is the most well studied and also obtained the most widely application material. It is good, however, it still has some limitations, so that's why people keeps iterating it, keeps adding some new alloys, new elements in it to improve its property. So the latest one is the nickel titanium cobalt. Compared with the previous one, the binary nickel titanium alloy, it is critical, but it has relatively narrow temperature, and it does not work well in low temperature. And if we add iron in it, this alloy behaves better at low temperature, but it's only available in small size. And nickel titanium niobium, it has wide temperature range, but it's also only available in small size. And nickel titanium hafnium, it works at high temperature, but it's only available in small size. The small size here refers to like around 1 millimeter or less than 5 millimeter diameter wire or thin strips. And to improve the property or find a cheaper alternatives for nickel titanium alloy, people developed that copper-based alloy. So the first generation, such as the copper zinc aluminum, copper aluminum nickel, these two alloys are brittle, and also later people developed that copper aluminum beryllium. These materials behaves good, but the beryllium is toxic. And at around like 2010, the copper aluminum manganese alloy. This alloy has low cost and is available in large size. And lastly, the iron-based chip memory alloy. The first several generations of it, such as the iron platinum, iron aluminum tantalum, these metals are very expensive. And the latest one starts from around like 2010, the iron manganese silica. This alloy has low cost and is available in large size. So in this presentation, I categorize the nickel titanium cobalt, copper aluminum manganese, iron manganese silica, these three alloys as the next generation chip memory alloy. And in comparison, and also since the firstly discovered nickel titanium one is the most widely studied, and this will be as a benchmark for the other three next generation chip memory alloys. So here's some pictures and pros and cons of the next generation chip memory alloys. Starts from the nickel titanium one. This material, the pros of this material is it has excellent energy dissipation and it is well studied. And the cons of this material is that it is expensive and it is hard to machine. Later, I will introduce some machinabilities of this material. We can see the details, how hard it is to machine this material. And also this material cannot work at low temperature, specifically lower than 0 Celsius. And nickel titanium cobalt alloy. The pros of this material is that it has improved strength and it has large size availability and it works better at low temperature. And the cons of this material is the same. It is expensive and it is hard to machine. So the pros and cons. And thirdly, the copper aluminum manganese alloy. The pros of this material is that it has low cost, it is easy to machine, it has large size availability, and it works in a very wide temperature, not only in low temperature, it also works well at high temperature, particularly at low temperature. And the cons of this material is that it has low strength and it has a dependence on the crystal orientation and it has a restriction on the largest manufacturing lengths. Currently the largest length available on the market is around 1 feet. And lastly, the iron manganese silica alloy. The pros of this material is that it has low cost, it is easy to machine, and it has large size availability. And the cons of this material is that this material is totally different from the previously three one. Is that this one it is more like a special stainless steel. It has low ship recovery capacity, and it is easy to have plastic deformation. So here's an overview of all the scholars around the world investigating the chip memory alloy. Mostly, all the scholars are distributed in the US, in Europe, and China, and also Japan. So as from this overview, you can see most of the scholars or the professors around the world, they focus on maybe like one or two compositions, such as Professor Andrews at UIUC. His research focused on nickel titanium niobium and nickel titanium alloy, and Professor Lagodas at Texas A&M, his research focused on nickel titanium hafnium and nickel titanium iron. And our research group is led by Dr. Saidi and also Dr. Genster. Our research group, we are one of the few research groups investigating all the 4 types of chip memory alloys in the world. So here I want to briefly introduce the test setup that is involved in all the experiments in this presentation. So later I won't repeat it again. So for all the material tests on a material level, we use an environmental chamber and an uniaxial material test machine. So when the low temperature is involved, we use a liquid nitrogen tank to cool down the material. And when the high temperature is involved, we just use the electric current resistance to heat up the chamber. And an extensometer is used to measure the deformation of the sample. And for the large-scale structural test, we use the large-scale reaction frame to perform the large-scale test. So enough with the background information. So here comes the next question. What chip memory alloy can be used for? Starts from the very beginning in the last century. After people first found the chip memory effect in alloy, it can be used as an actuator for robotics arms and foldable solar panels, or the actuators for planetary rover or robot. It just can be involved in anything that needs to change the shape or that needs to have to change its shape, like a transformable like structure. So here's the schematic of how the chip memory alloy actuator works. So if it starts from the cold temperature and the initial length, and if we give it some kind of like biased force, it can be either gravity or like a biased spring. It will have some deformation in a deformed shape. It is in a cold state. And if we heat this material up in a hot state, the phase transformation will occur. And this material will shrink and generates an actuation force. And this shrink, the distance change is called the actuation stroke. And the magic thing is that this material can not only shrink by itself, if we close it down, it can expand again. So this is a reversible and repeatable process. So that's why it can be used to make an actuator. Chip memory actuator is not the only solution, because so far we have so many actuators, such as pneumatic ones or hydraulic ones, or even human muscle is the most simplest actuator. The hydraulic actuator or the pneumatic actuator, the problem of them is they work well on the Earth. However, if on the deep space, they need a really heavy and strong pump. Mostly it's heavy. They cannot, use a rocket to send this pneumatic pump or the hydraulic pump on a space station. So the chip memory alloy becomes one of the best solution. So here's the work density comparison between the conventional actuators and chip memory alloy. For pneumatic actuator, it has really low work. It's around 0.2, hydraulic 5, human muscle 0.04, and for chip memory alloy, it can be up to 10. So it's like around twice of the hydraulic actuator. So here's an example of the chip memory alloy actuator. So this is the loading condition we use. We fix one end and give this material a constant force, and there will be a deformation. And if we lower the temperature down, it will shrink back. So this force and stroke is the target in this stress strain curve. So firstly, we will look at the nickel titanium chip memory alloy. So if we lower if we start from like minus 80 Celsius and heat it up to 80 Celsius and then cool it down to 80 Celsius, do it repeatedly, or just this is one cycle. We can do it repeatedly. Under a constant tensile stress of 100 megapascal, the actuation stroke, that is this deformation of this material, can be around 4%. So this is good enough However, for copper aluminum manganese alloy, and under the same gravity load, 100 megapascal, and this material works from around minus 120 Celsius and ends up with around 0 Celsius. And the magic thing is the impressive thing is that it can generate a stroke of more than 10%. So this is really suitable for the space applications. And the key for the chip memory alloy application includes two parts. The first is the temperature range. The second is the actuation stroke. It's also the stream recovery capacity or the deformation, the total the difference of the deformation this material can generate. So here's the like a comparison of the temperature range of different chip memory alloy. I divided into like minus 100 Celsius. This is mostly for the space like extraterrestrial applications, and minus 40 Celsius maybe for the Arctic or in Alaska. 0 Celsius to 20 Celsius. This is maybe for the room temperature. 50 Celsius. From minus 40 Celsius to 50 Celsius. This is the temperature range we think that can cover most of the bridges and structures on the Earth. And above 100 Celsius, this is for some kind of like airplanes or the jet engines. So here's the comparison of the temperature range of these 4 chip memory alloys. For nickel titanium alloy, it works from around 0 Celsius to 50 Celsius. And for nickel titanium cobalt alloy, we can see it's the low temperature working range extends a lot, maybe to around minus 60 Celsius. For copper aluminum manganese alloy, this material works from minus 120 Celsius to around 70 Celsius. And for iron manganese silica alloy, it works from minus 40 Celsius to like around 100 Celsius, maybe 160 Celsius. And here's the stream recovery capacity of different chip memory alloy. For conventional nickel titanium alloy, it can generate a stream recovery of around 5%. For nickel titanium cobalt, almost the same, a little bit higher or lower than around 5%. For copper aluminum manganese alloy, it's around 10%. And for iron manganese silica alloy, it's around like 1% or less than 1%. So I briefly introduced the introductions in applications in actuators. So next, what else can chip memory alloys can be used for? It can be used as the dampers or recentering elements in automobiles or in also in space rovers. Actually, in this figure, this is a picture from NASA, and this the tire of this space rover is made of nickel titanium wire mesh. How does the chip memory alloy damper works? Here's an example. This is in the structures, and also if we scale it, we can also use it in maybe in a space rovers. So here, this cable, this tilted cable is the chip memory alloy, nickel titanium wire strand, and the chip memory alloy here mainly offers the self-centering capacity, and there's some structural bolts that creates the friction, and the friction is used to dampen the energy. So here's on the stress strain curve, the superelastic effect of the chip memory alloy generates a flag-shaped stress strain curve, and the dampings and the frictions from the bolts generates energy dissipation. So this is final behavior of this chip memory alloy dampers. So next, I will introduce some key parameters of the chip memory dampers. Before I jump into that, I'll quickly introduce the key parameters of a typical stress strain curve. There are several parameters we care more, so such as the yield strains and the elastic modulus, the residual strain, and also the recovery strain, and energy dissipation, and the fracture strain. The recovery strain is maybe the most important one here, because this is what differentiates the chip memory alloys from conventional metal. It's if we unload it from some point, how much strain it can recover before the residual strain accumulates. So the key for the chip memory alloy damper applications includes its strength and ductility, temperature dependence, fatigue resistance, loading rate effect, and machinability. First, here's a comparison of the nickel titanium cobalt, nickel titanium, and copper aluminum manganese alloy. This is the monotonic stress strain curve. We see that the copper aluminum manganese alloy is around like 250 megapascal, nickel titanium around 450 to 500 megapascal. This is comparable to conventional steel. And for the nickel titanium cobalt, it can be as high as 650 megapascal. So time is limited. I'll speak a little bit faster because I have so many things to present. So the temperature dependence. Next, we'll move on to the temperature dependence. As we previously mentioned, the temperature is a very important parameter affects the behavior of ship memory alloy. So this is the most widely studied nickel titanium alloy. So starts from the room temperature. We see that the loading protocol we used here is we just used a 1% stream controlled incremental cyclic loading to 1% unloading, loading to 2% unloading until 5%. And here we see that room temperature up to 50 Celsius, this material is still exhibits good ship recovery capacity. There's almost no positive residual stream. And we see that as the temperature increases, the yield stress of this material increases significantly. And the same, when the temperature decreases, the yield stress also decreases significantly. What is not very good is that when the temperature drops to 0 Celsius, this nickel titanium alloy starts losing the ship recovery capacity. After we unload it from 5%, the residual stream is around 2%. That means this material is losing its function. Down to minus 20 Celsius, it behaves almost like a regular steel. So we pause the test. So this is the nickel titanium cobalt alloy. So also starts from the room temperature. As the temperature increases, the behaves almost the same as the nickel titanium alloy. What is impressive is here when we lower down the temperature to 0 Celsius, minus 20 Celsius, until minus 40 Celsius, this material still exhibits really good ship recovery capacity. Unloading from 5%, the residual stream is almost like it's very close to 0. That means as temperature pulls down to minus 40 Celsius, this material still exhibits around like 5% of stream recovery capacity. This is really advantages for bridge applications for the cold regions. Here comes the copper aluminum manganese ship memory alloy. The rest of the thing is the same. For this material, it behaves better it behaves really good at minus 40 Celsius room temperature and 50 Celsius. What is really impressive is that I tried to lower down the temperature to minus 100 Celsius. This is has exceeds the temperature range on the Earth, but this material still exhibits really almost 100% of stream recovery. So this indicates the great potential of this material for the deep space applications. So here's a comparison of the three materials. This curve shows the yield stress dependence on the temperature. So we used a linear fitting for these three materials. The larger the dependence on temperature means that this material is the yield stress is more sensitive or has larger dependence on the temperature. For nickel titanium and nickel titanium cobalt, the dependence is around like 7 megapascal per Celsius. And for copper aluminum manganese alloy, it's only around 2 megapascal per Celsius. That means this material is more stable at different temperatures. As the temperature reduces, its yield stress does not reduce much. So next, I'll briefly introduce the loading rate effect. For seismic application or some other types of vibration control, the loading rate might be an important factor. So for nickel titanium alloy, this material is sensitive to loading rate because when we use the high loading rate to load this material, it's like generates adiabatic condition for the material. That is, the inside of this material the temperature will raise up. And for nickel titanium alloy, the hysteresis loop will narrows down, and also the yield stress increase a little bit. And for copper aluminum manganese alloy, this material is very stable. When the loading rate is up to like 15 Hertz, and we see that the hysteresis loop has like very little or negligible change. So the research on the stream rate of nickel titanium cobalt is still underway. So I'm expecting to say this material behaves very similar to nickel titanium alloy. So next is the fatigue resistance. So here is what we did. The fatigue resistance is important because for some kind of vibration for dampers or bridges, earthquake engineering, or the dampers in automobiles or in the space rovers, the cyclic loading, constant cyclic loading will use premature failure or functional or the function degradation of this material. Here, the loading rate we used is 5% constant strain loading, just loading, unloading, loading, unloading until the material fractures. For the nickel titanium chip memory alloy at room temperature, it starts from at the first cycle. This C means cycle. The first cycle it has 100% strain recovery, and after around as the loading cycle increases, the yield stress decreases. And the good news is that the strain recovery has almost no change. After around 100 cycles, this material fractures, it still exhibits 100% of the strain recovery capacity. So this is what the nickel titanium cobalt alloy will behave like. The yield stress is much higher, and the degradation is almost comparable to the nickel titanium alloy, and this material fractures at around 43 cycles, meaning that indicating that this material might have a lower like fracture toughness or something, but we haven't tested yet, just a speculation. Here comes the copper aluminum manganese chip memory alloy. This is really impressive here because even though this material has really low yield stress, but as we can see, this material withstands 50,000 cycles of 5% strain. This is really, really impressive. This has definitely exceeds the demands for earthquake engineering, maybe better for some other like vibration control dampers. So lastly is the machinability. Machinability is that it's important because for practical applications, we need to process the chip memory alloy into the design shape, such as tubes. We need to add stress on it, and also it increases the cost of using this material. So this is the difficulty of machining traditional nickel titanium alloy. So here's some example using a CNC machining. It has a welded chip, and sometimes the insert just disappeared, and also the workpiece, the final workpiece has really low quality. And the reason for this, one of the reasons is that the nickel titanium alloy has really high hardness. In this figure, this shows the weaker hardness comparison of the different chip memory alloys. For nickel titanium alloy, it's more than 400. For mild steel, it's around like 270 or 230. And for copper aluminum manganese alloy, it's around like 280. And for stainless steel, it's 320. So CNC machining is still the most widely used machining method because it's the easy obtainability. And the key parameters for the CNC machining includes the machining temperature, the tool wear, the workpiece surface quality, and also the workpiece surface quality. Here I'll briefly introduce the machining temperature of the comparison of the nickel titanium alloy and the copper aluminum manganese alloy. Here the cutting temperature, first figure shows with different depths of cut. The second one shows the different feed reach. The depth of cut, feed reach, and also the cutting speed. Here we use this the commonly parameter we use to machine conventional mild steel, just to see what will happen if we use the commonly parameter to machine this chip memory alloy. Here we see that the cutting temperature of the machining the nickel titanium alloy can be as high as to like 600 Celsius. At this temperature, this material will just melt and weld it on the insert. And the machining temperature of the copper aluminum manganese alloy is around only like 1/3 of the temperature for the nickel titanium alloy. Here I need to emphasize that the machining temperature of machining nickel titanium alloy is so high does not mean that every time we machine it the welding happens. How we do this is we need to reduce the cutting temperature. That means if we machine a mild steel, it takes like 1 hour. We cannot machine the nickel titanium alloy within an hour because it will melt. So that's why we need to machine the nickel titanium alloy within like a week. Just increase the duration, lower down the cutting speeds. This also increases the cost. So here's a comparison of the tool wear. Here from this figure, there are 3 materials: the copper aluminum manganese alloy, nickel titanium, stainless steel, and mild steel. From this figure, we see that the machining copper aluminum manganese alloy is almost comparable to machining stainless steel. It's a little bit higher than machining mild steel, but it is only around like 5% or like only 1/20 of that machining nickel titanium alloy. Here's the comparison of the workpiece quality and From this figure, we learned that machining copper aluminum manganese alloy is the final product. The quality, the surface roughness, and the diameter deviation is almost comparable. The final surface roughness and the surface quality and the diameter deviation is almost comparable to mild steel. So here comes the third part, the sheet memory alloy in earthquake-proof bridges. So here's a picture of the world's first flexible bridges using sheet memory alloy. It's been constructed in Seattle. So this project is led by Dr. Saidi and Washington DOT. So in earthquake-proof bridges applications, the sheet memory alloy can be used as reinforcement. This gold part is a sheet memory alloy, and also it can be used as a post-tensioning tendons in the middle as a red line in this figure. So the reason why we need to use sheet memory alloy in the bridges is that for conventional reinforced concrete columns, it has some limitations. Is that after the earthquakes, the bridges may not collapse, but it will have really large permanent drift, such as the drift here. So for this is because this is a stress strain of the conventional steel. After unloading it, the steel will exhibit a lot of plastic deformation, and this residual strain of the steel will yield the final force displacement curve of this column looks like this. So there will be large residual or permanent drift of this column. Even though this column is not collapsed after the earthquake, during the construction, reconstruction, or the something else, the transportation is affected, we still need to demolish it. So that's why we need to reduce the permanent drift of these columns. So here comes the sheet memory alloy. There are two types of earthquake-proof bridges using sheet memory alloy. The first one is we can use the sheet memory effect of the sheet memory alloy to provide the post-tensioning. We put a sheet memory alloy tendon in the middle, and when the earthquake happens, it will generate the self-centering forces to pull the columns to the original position. And this is the final expected force displacement curve or force drift curve of this column. It will has much reduced permanent deformation. And the second method is using the superelastic effect of the sheet memory alloy to provide the self-centering. We put this red curve is the sheet memory alloy. The black curve is just regular steel. We put the sheet memory alloy in the plastic hinge region, in the bottom region, and when the earthquake happens, the superelastic effect of this material will also push back the column into the original position and lead to a flag-shaped force displacement curve with negligible permanent deformation. So of course, this is sheet memory alloy is not the only option. Here are some other options, such as blocking column with blocking foundation, replaceable rubber plastic hinge or isolation, or we can add in braces. So next, I'll use an entire section to introduce the advances of the post-tension columns with iron manganese silica alloy. So here it is referred to, for brevity, it is referred to as iron sheet memory, iron SMA. So here's the traditional post-tension columns. For traditional post-tension columns, we can use high-strength steel strands or the fiber-reinforced polymer FRP tendons, such as this blue line in the schematics. The problems of the limitation of the traditional methods is that for the FRP or the high-strength steel tendons, they only works even though they have really high strength, we only use the elastic range of it, because after the elastic range, the FRP may fracture or the high-strength steel may exhibit plastic deformation. So only the elastic region is effective. And if we only use the elastic region and the force displacement curve of this column will behave like this, there's no energy dissipation of this material. So that's why we need to add, we still need to, in addition to this FRP or high-strength steel tendons, we still need to add some energy dissipation elements, such as this brown part here. After adding the energy dissipators, the behavior, the stress, the force displacement curve is what we want. And the main challenge of using the traditional post-tensioning methods is that really heavy hydraulic devices are needed for on-site construction. this is unavoidable, which so this is the main challenge of the traditional methods. So here comes the sheet memory alloy. If we're using the iron sheet memory alloys, this problem can be solved. Starts from the original shape. If we stretch it to some kind of deformation, and the first two steps we can do it in a factory or in a laboratory. We can use the heavy hydraulic devices, but it's not needed to be onset. And then we can put this stretched iron SMA into the column. Here comes the onset construction. We just put this tendons in a column, and then we just apply some heat stimulations. It can be either electric resistance heating or using some kind of heating tip, and recovery stress or a post-tensioning force will be generated inside the material. So that means for the onset construction, there's no hydraulic devices needed at all. Time is so limited. So this is what happens on the material levels. So maybe I just skip it. So based on the above methods or the concept we proposed, actually led by Professor Saidi, we proposed a new post-tensioning columns concept. It's just showing here. We use a iron SMA tendon in the middle and use the regular steel as the energy dissipator. And the expected stress strain force displacement curve is like this. So the key of applying this, or the restrictions of making this bridge column true is the follows. First is the strength and ductility and the temperature dependence. And also we need to increase the post-tensioning deformability, post-actuation deformability, the fatigue resistance, and also the reliable anchoring. So here's some stress strain curves of the iron-based SMA. So from these stress strain curves, we see that this material mostly is more like this stress strain curve is more like a regular stainless steel. But what is impressive here is that this material is really ductile. The fracture strain can be as high as 50%, and also it works from -40 Celsius to 50 Celsius. Here's the cyclic stress strain curve of it. What we did here is just we applied 1% increment until failure, just 1% increment, loading it to 1%, unloading it to 2%, and then unloading until the fracture of this material. At all three temperatures, -40 Celsius to 50 Celsius, this material still exhibits really good ductility. And another thing we learned here is that as the loading cycle increases, as the loading amplitude increases, this recovery strain also increases. This is important because this reflects the transformation degree of this material. When we increase this loading amplitudes from 4% to 20%, the recovery strain almost like doubled. Based on this finding, we found a way to increase the post-actuation deformability of this material. And because if we increase the pre-strain levels, we are sacrificing the total deformability of this material. So just to ensure increasing the pre-strain level is feasible for practical application, what we did here is when we increase the pre-strain level from 4% to 25%, of course the strain recovery doubles. This is what we know. But after this, we stretch this material monotonically to failure. We see that this material still exhibits more than 15% of deformability. That means increasing the pre-strain, it is not only a feasible way, but it's also a safe way. So next, we also did the fatigue loading on this material just to simulate what will happen for the earthquakes. So we see here for like 20% of pre-strain plus 1% fatigue. This is more than what we need in a bridge column. And we see here after around 500 cycles, this material is still stable, and there's still no fracture. And after the low cycle fatigue loading, we stretch this material to failure monotonically. It still exhibits around 10% of fracture strain. That means this is still comparable to the conventional steel. Lastly is the reliable anchoring. So the anchoring is this black part on top and the bottom of this column. So this is important because once the material is being heated up a very large post-tensioning force will be applied on the column. This anchoring is the end of this bars that needs to ensure the column is being post-tensioned. The conventional methods includes we can use the shear stress, the shear screw bar locker, or we can spread it the bar and use the concrete to embed it. Just use the friction to anchor the column. These two options is okay, but the problem is that the shear screw will lead to stress concentration, and also the straightening of this lumbar increase the cost, and also this is not very flexible for on-site construction. So we start thinking about maybe we can use welding for this one. So we developed a new welding anchorage method using MIG welding. What we did here is we used a stainless steel rod, used the machining to drill a hole in the middle, and drill two slots on the side. And if we put the iron SMA bars in the middle, we can add welding lines in this slot. So to test if this is feasible, we did some material tests, and from this results we found welding this material does not reduce its ductility and also the strain recovery capacity. The fracture strain is still as high as like 30%, and also it exhibits around 300 megapascal of recovery stress, and it is still very ductile. So once we got the confirmation from the material test, we developed a new anchorage concept for the large-scale bridge applications. So here's the anchorage concept we developed. It's still the stainless steel. It is still a stainless steel anchor. We see there's a pedal pattern here. It's like for the large-scale applications, we need not only 1 bars, maybe we need 4 bars, 6 bars, maybe 10 bars. Using this concept, we can add as many bars as we want. And the second step is we pass through the iron SMA bars in the middle, and then we can apply the machining, the welding in the welding slots, and then these bars are anchored to this the anchor, the stainless steel anchor. To test the reliability of this the proposed anchorage concept, this is what we did. We just use a two-way central hole hydraulic cylinder to stretch the bars. Both sides are welded by the proposed anchor. In the middle is the iron SMA, and we just stretch these bars to 20% and 10%. We did 2 tests. Here's the results. Here I need to emphasize, maybe from this figure you cannot see how large this is, but when I was working on site, this is around like maybe 12 feet. And the force here is more than 200 kips. When we are doing this, we are so nervous. So maybe we are the first person doing, when we are doing this, if this bar structure here, we are just, producing some kind of bomb. So we are so nervous. But fortunately, after this test, both of the 20% pre-strain and 10% pre-strain, the bars are still intact. So we are okay. We found this is reliable. And so after confirming all the feasibility of welding and also the anchoring, so here we constructed 2 columns, 2 1/3 scale bridge columns. The first one, the iron SMA 10 with the 10% pre-strain bundle, and the second one with a 20% pre-strain bundle. The construction process of this column is almost the same. We have a pre-stressed conduit in the middle, and then we put the iron SMA bar in the middle, and we wrap the heating tapes around the bars to heat the bars up, and we put a load cell to measure the post-tensioning force. So here's the setup we used for the seismic loading. We applied quasi-static loading to simulate earthquake loading condition. And this is the column, and also we use a lot of gauges to measure the response of this column. Here's the force drift response of this of the 2 columns we measured compared with the reference RC column. The red one and the blue one is the column we tested, and the black one is the column with exactly the same with the same design, material properties, and dimensions. So we are making comparisons among them. From this curve, we see that the 2 iron SMA columns, they exhibit higher strains, and also after unloading from the same applied drift, their residual drift is much smaller than the reference RC. So here we extracted the residual drift versus the applied drift. Here, let's see, for example, at around 8% applied drift, the residual drift of the reference RC is around maybe 7%. But for the two proposed columns, they are around maybe like 4.5%. It's only the residual drift of the proposed columns are only around 60% of the conventional design. So this means this column, the proposed column, is definitely feasible and improves the seismic resistance of the system of the column. And here's the normalized pre-stress degradation. During this test, it is noted that we loaded the column until 9.5%. This is really large really large drift. And up until the end of the test, both of the columns, the iron SMA bundles in it, they remain intact. And then here's the normalized pre-stress degradation of it. Until we loaded these columns to 9.5%, the degradation in the pre-stress is less than 15%. Means the column is the post-tensioning is there until the end of the test. So here's a comparison of the displacement ductility. The displacement ductility of these two proposed columns is around like 7, and for the conventional column, RC column is around like 307. So there's a significant improvement of the displacement ductility. So next, I'll introduce the advance of the self-centering columns with superelastic ship memory alloy. So as mentioned before, there are two concepts. I introduced the first concept. Next, I'll move on to the second concept. So how does the superelastic ship memory alloy makes the column earthquake proof? So as mentioned before, the superelastic ship memory alloy is put in the bottom, the plastic hinge region of this column. The rest of them just steel and normal concrete. This blue part is the engineering cementitious composite. It's the ECC. Because we know the ship memory alloy, they can deform in maybe up to 10%, but the concrete cannot. If we load this column to maybe like 20% of the drift ratio, the concrete spalling or the tensile cracking will just reduce the capacity of this column. So we need some kind of high performance cementitious material here. The reason why we use ECC here is that the ECC has really high tensile strain. Its tensile strain is maybe like 20 or 30 or even 100 times higher than the conventional concrete. And also it has spalling resistance and low permeability and long durability. Actually, this concept is proposed by Dr. Saidi, not mine. Just I'm introducing it. So this is the final expected force drift response of this column. So we are expecting to see almost 0 residual drift. That means this column can be completely functional after the strong earthquake. So for this concept, there are a lot of studies conducted before, mostly by Professor Saidi. So maybe back to like 2009, and also by Dr. Ginsterk. And we can either use nickel titanium ship memory alloy in a plastic hinge, or copper aluminum manganese ship memory alloy in a plastic hinge, or use the copper aluminum manganese ship memory alloy plus the replaceable ECC plastic hinge. So here's some the expected stress strain, the measured force drift response of the column. So the first one is the nickel titanium column compared with the RC column. Here we see that compared with the RC column, the residual drift of the ship memory alloy column is much smaller. For the copper aluminum manganese column, it has lower yield strength, so maybe the capacity is lower and also the stiffness is lower. But speaking of the recentry capacity, such as the residual drift, it is still really good. So what I'm doing now is we are doing some studies on the novel nickel titanium cobalt ship memory alloys. This research is still ongoing. In this research, we are going to test the feasibility using a superelastic nickel titanium cobalt ship memory alloy in the bridges, and 2 1/3 scale bridges will be tested, and practical connections between the ship memory alloys and the steels will be studied. So here's some like quick view of this study. I won't go into details. Just the first problem we need to solve is we want to use the high coupling to connect these special alloys into conventional steel, and then we need to run a material test to test the material behavior of this material, and then last we will put this material in a plastic hinge of the column and then test the seismic performance of this material. Okay, I went really fast. So above is all the research I've done so far, and also other professors' research, mainly by Professor Saidi and Professor Tazav. And here's the bibliography for the publications involved in this presentation. So far, we've produced 12 papers on the sheet memory alloys. 7 of them have been published, and there are maybe 5 or 6 of them are still in the pipeline. And last, I really need to acknowledge my advisor, Dr. Genster, and also my maybe co-advisor or collaborator, Dr. Saidi, their unreserved help in the past 5 years. And also our collaborator, Professor Raki and Dr. Casey from Japan, and also Professor Taza gave me a lot of help, and also the rest of the sponsors and material suppliers. And that's all for my presentation. Thank you so much for your time.
Thank you so much for the presentation. Now we're open for questions for Dr. Hong. Go ahead.
Thank you very much for your presentation. So I have a question regarding a couple of slides, but one's essentially where you talk about the resistance, different sheet memory always, and presented the experimental groups. So there on your loads, you have strains, x-axis. Some of your curves are going to this negative values. So can you explain a little bit more about this?
That is a really, really good question. Let me go back here. Actually, I'm preparing. Actually, we just submitted a paper on this phenomenon. This is under review. It is here. So I didn't have the schematic here, but what happened is here. This is what we are expecting here. So after we loaded 5%, unloaded, it will end at 0. But for this material, we see that if it starts from 0, loaded 5%, unloaded, it will go to minus 0.50. The reason for this is that for the nickel titanium alloy, during the manufacturing, because when manufacturing these materials, there will be a lot of extrusions or rolling or like cold workings on it. It will leave a lot of useful phases in it. So that means before we start this test, this material has been deformed in some way, some kind of residual phases in it. So that's why when we load it to some point and then when we unload it, we somewhat trigger the residual phases in the material.
So do you expect this is something like very negative in later applications? If, for example, it's something significant, expect that this effect can be better for some other application.
Yeah, I understand your point. Actually, I didn't point it out here because we don't consider this is negative, because actually this is advantageous. What we are concerning is, as we can see for this material, after loading to 150 cycles, the stream recovery is disappearing. This is negative. But if it is increasing, that means if we put it in a column, let's say if we put it in a column, after the earthquake, the self-centering actually improves. It is more self-centering. Actually, this is what we want. Maybe for some other, maybe like delicate applications, this might be negative, but so far for the bridge applications, this is advantageous. Yeah. Thank you for your question.
Any other questions?
Go back to the diagram that you used to show the flow extension.
Yes.
So I know because I work in the industry as bridge engineer, and I know typically like if we have like multiple columns for bridges, that sometimes we use like a single slab footing to connect all of them. So are you guys planning on doing research to see the effect of multiple columns on a single slab? Or is that something that you've ever thought about?
Are you talking about the longitudinal direction or the lateral direction or the transverse direction?
In terms of like, if you have multiple columns for like a pier,
Yes.
so you'll have basically multiple post tension within the columns.
Yes.
But sometimes what they'll typically do is they'll make one single footing that connects all the columns together.
Yes.
So are you guys planning on doing research and seeing the effects of multiple columns with a single footing besides this? Because you only have a single footing with one column.
I see your point. Actually, I don't think the footing is a problem here because actually, let's see if this is a 2-column. My question is if you are considering this way or in this way. If the footing is just a platform, maybe they are a single or separate or combined footing. I don't think this will be a problem. We haven't done this research before, but This won't affect the response of the entire bridge, right?
Yeah,
Maybe I'm wrong, I'm precisely.
I don't know, just-
No, I agree, just,
Yeah,
because the flexible element here,
yeah,
the column, right?
Yes.
You have one column or you have multiple columns.
yes. Yeah, okay. Thank you for your question.
So the master design is looking to tap into this capacity protector. So that those guys are not going to do it, wait to solve one.
Yeah, because you see, it is separated here. Back to your question, maybe the problem, if you make this foundation really, really big, the problem will be the anchoring. You need to consider how to anchor these things in a big platform. But in a single platform, you just need to,
Keyword is, as Dr. Tazar mentioned, the footings and capping should be capacity protected, meaning no yielding.
yes.
Meaning, so all the yielding, all the plastic deformation will take place in the column.
I do have many questions. Go to slide 29 or 30. And that's not that, that's fine. Okay, so we know that these materials are temperature
Sensitive.
dependent, right?
Yes.
And there's something called, I'm sure you know, AF or austenite finish temperature.
Uh-huh.
You're comparing three different alloys. Did you keep their AF the same? So you're saying
Uh-huh.
NITI didn't work well at -20. What was the austenite finish temperature?
Oh, I see. Thank you for your question, Professor Tazar. We indeed did some DSC tests to measure the austenite finish temperature of this one. I can tell you the answer is that for this one, the nickel titanium ones, the austenite finish temperature is 0 Celsius. And for the copper aluminum manganese alloy, the AF is, I think it's -40 Celsius.
So then you're not comparing apple to apple. You already have a material that
Uh-huh.
works better in cold, and now you're saying the material is not supposed to work in cold, it's not
Uh-huh.
working in cold. So you need to keep the AF of all of these alloys the same,
Uh-huh.
then you can play with the temperature range.
I see
So
your,
the one that the Versailles put in the bridge was -10.
Mhm.
Degree Celsius. Means that up to -10, it is superlasting. Going lower than that, it will have some residual effects. And
So AF is something that they control during manufacturing.
exactly.
it is intrinsic, yeah.
So we need to test them the same AF from the manufacturer. If the AFs are significantly different, like 0 and -40,
Mhm.
you cannot compare the temperature.
Yeah, actually, Professor Tazar, there's a few things I want to emphasize on your question is that the austenitic finish temperature is some kind of intrinsic property of this material.
Yes, but.
We can control it. Yeah, we can control it, but you see, let's see, if the manufacturer can lower down the nickel titanium alloy to -100 Celsius, they don't even need to develop copper aluminum manganese alloy. It is controllable, but it is really different. Maybe for the nickel titanium alloy, I think they can lower it down to -10 Celsius. I never see an AF lower than -10 Celsius for nickel titanium alloy. But for nickel titanium cobalt alloy, it is very, very easy to reach -60 Celsius.
Perfect.
Yes.
My point is then you cannot compare beyond their AF.
Okay.
So below their AF, you should say not applicable. Because.
Oh,
they're
yes.
not-
Yes.
Because they are not supposed to work beyond
Yes.
that.
Maybe I should add a note here. This is the lowest minimum limitation of their AF. Yeah. I didn't look into I'm not a manufacturer and I cannot control this. So I'm just discussing what is available on the market. That's the intrinsic property of the material.
Thank you.
Yeah. Thank you for your question. Yeah.
Those came from Japan, right?
Yes.
FDD.
Yes.
The ones that we use in Seattle were from the US.
Yes.
Are there any other questions? Oh, go ahead.
Thank you for the presentation, great job. Your comment about your test that was potentially a bomb in the lab struck me. So you created that tensioning clamp.
Yes.
And you did it by creating slots and then MIG welding,
Yes.
right?
Yes.
How did you verify the penetration of the weld? Because it's hidden. That
Yes.
would scare me too, if I didn't know how well
Uh-huh.
I had penetrated that actual rebar.
Yes.
How would you do that in the field or at all?
Okay, yeah, thank you so much for your question, yeah. So what we did here, yeah, as you mentioned, first, what we did here is we keep adding more steps, we just repeat doing it. So firstly, let's see, back to your question, how do we confirm welding is effective
Right.
throughout, like, it's uniform throughout this material? What we did here is we start from a single bar, this is 18.7 inch diameter, this is the first test, we did it. From this tentative results, we found that this is reliable. And then we're doing it in a bigger anchor with 4 slots. We found this is still visible, and also during welding, the technician, they can tell it by experience, but this is only empirical. They can tell the tip of the welding arc if it is good or not. So from this one, from the welding results, this is good. It looks good. And then we did another test. The test it in this is a 4 scale, just to do it. After loading it to 200 kips and to 20%, this is more than what we need. It is still safe. So this is what we did, like a practical way to ensure this is safe. And back to your question, actually, if we are looking at the macrostructural level, this will be my next paper. I'm indeed doing research on this. We need to maybe cut this one in half and do some metallography analysis on it. We just maybe, I think 2 weeks ago, our lab just bought a new microscope. I'm doing it recently. So this will be the next step. So because for this project, we are mainly focusing on column, on the bridges. We want to make sure the bridges will work. So far, I think we did both material level and the structural level, the small scale and the big scale. We consider the most severe and dangerous conditions. So we ensure this is safe. But speaking of the mechanisms, it will be like will be our next step. Yeah, thank you.
Did SMA like the welding?
Oh, yeah, for iron SMA, it is okay. But for all the other, like nickel, titanium, cobalt, or the copper, aluminum, manganese, they don't like it. So one of the reasons people use this iron SMA is that this is special. This is just like a special stainless steel.
Yes. Can you elaborate on what you mean by it did not like the welding?
I'm sorry?
I can say.
Oh, yeah.
Yeah, we did some tag welding here and put it in the machine, and all of those tags boom, 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 came out.
Oh, just immediately, bro.
Yeah.
Oh,
Yeah, it just doesn't like it.
oh, it just doesn't connect. Oh, all right. Sorry, another question?
Quick question, thank you for the presentation. Could you please bring up the slide in which you compare the historic behavior of the column with and without it?
This one?
That's 60 something. Yes. So, further is on the left one here, when we use the material, the SMA, should we expect less energy absorption because pinching here when we use it, the SMA is much more pronounced in compared to typical RC column? Is it the downside or?
Yeah, thank you for the question. This is actually a sacrifice. This is a sacrifice. You see it, we want to reduce the permanent deformation. That means the pinching definitely needs to reduce the energy dissipation. So maybe this can be a drawback, but maybe if we want to improve this, maybe we need to consider like on a design level, like how to control the bars of it, ensure this reduced hysteresis loop is large enough for the energy dissipation. Yeah, this is a sacrifice and unavoidable sacrifice.
And not the design level. When there be 5% action, that's very design level. But when you use the titanium, we recommend 3.2% damage. But the design level it can be.
My second question is that, okay, I know that this material can help a lot in terms of the cell centering.
Yes.
Can combine these with, for example, less expensive systems such as EERI to reduce the residual effect after the airspace. But my question, how practical it is, because I see how temperature dependent this material is, and for a place like Reno, you have temperatures down at -20 in the winter up to 45 degrees in summer. So if an earthquake happened 2 a.m. in January, is it going to affect the performance of our structure in compared to the one happened at noon in mid-July when the temperature is much more higher?
Okay, I understand your point. So maybe we should back to this that. Yeah, I think the basic mindset is that if we are designing this, if we are using this one in the real bridges, we always need to design based on the most dangerous and most negative condition. So here, let's say if it's for this material, for the nickel titanium cobalt one, if we want to use it in somewhere that's in California, no cold winter, no cold temperature involved, we don't need to consider this region. But if you want to use it here, maybe we should design based on this yield stress.
Do you use the most critical, for example, temperature and design based on that?
Yes.
To the point that you may decide not to use this in Alaska.
Thank you.
Thank you. Yes, Professor.
All right, one last question.
Just because you're on this slide, I was just curious. So mainly you have characterized the materials, which is really understandable on experimental tests. And here you're showing just one test, right, per scenario, temperature when you vary different parameters. And I was wondering, how many tests did you perform for each condition? And what consistency you observed across, just different tests under the same condition? Which goes back to some extent to how reliable
Yes.
these materials can be in conditions, real conditions that are going to be different from the high controlled one
Yes.
we have in a lab.
Yes. Yeah, thank you for your question, Professor Petrol. Actually, to answer your question, I have to tell you, I tested maybe I think more than 500 or 1,000 of these materials. More than maybe I think at least more than 500 dot bones. Here I show you the results. Let's see, just for this test. For this test, I only have three results here, but I have maybe 3 papers. I think for these 3 cases, I have more than 70 samples.
Per condition.
Oh, in total, maybe each condition I tested up, I think in our previous test, each condition at least 3 samples. And also we tested different conditions, always consider the most dangerous ones. The
Yeah,
repeatability.
it's really this plot, you moved to the correct slide, so it
Yes.
caught my attention, looking at the spread of strains you see.
Yes.
Right, under apparently the same material and, same, temperature. And so I
Yes.
was wondering if that's something, you observed here,
Yes.
but in general, it was more consistent that numbers the other
Yeah,
tests.
this is really feasible concern. Actually, Professor Yi and also Professor Genster, my advisor, they excluded at the very beginning. I need to do more tests, more than enough, more than we need to ensure it is safe and it's reliable and repeatability. I tested so many.
It's a new material when you get to comfort level.
Right. So, so your targets go above 3 per condition, right?
Yeah,
So
at least
you have a kind of statistically significant population of records,
Yes,
data for.
yes, yeah. All the results I prepared here is the most typical one and the safe one.
Okay, with that, we'll wrap up questions, but if you have any more, I'm sure he's happy to answer afterwards. Otherwise, thank you so much, Dr. Hong. Before please eat, let's let everybody get a slice and then figure out where we're at. Good job, man. That's good.
Thank you.
Here, let me stop the Zoom. Oh.